We looked at the law of sines, and now we're going to be looking at the law of cosines. So for the law of cosines, we also use that to solve oblique triangles. Now remember, oblique triangles are basically a triangle without a 90-degree angle. A couple other things. This is good for two cases, side angle side, and then also side side side. So side angle side, as an example, would be we are given two sides in the included angle. Now it can be any two sides in the included angle, not just like the picture I have drawn here. It could work for any of those. Now last case is side side side, meaning I know three sides and no angles. So that's what the law of cosines is good for. Now the law of cosines is a little bit more complicated than the law of sines, I think. So you want to make sure that you put these on your note cards. There's actually a pattern here. A squared is equal to b squared plus c squared. So that's going to be the other two sides minus 2 times the product of the other two sides times the cosine of the angle across from whatever is here on the left. B squared is equal to a squared plus c squared minus 2ac cosine of b. C squared. And again, these definitely need to be on your note card. You're going to be referring these to a lot, so that'll be important. We also have another formula that we'll want to use here. This is called Heron's formula for the area of a triangle. Now you say, well, we already know the area of a triangle is 1/2 base times height, but this is specific. This is Heron's formula for the area of a triangle when three sides are known. So when we have three sides, side, side, side. So the area of the triangle, first of all, with Heron's formula, starts with the semi-perimeter. Semi-perimeter we'll denote with an S, and it's equal to 1/2 times the sum of the three sides. Then once I have that value, the area then is going to be equal to the square root of the semi-perimeter times the semi-perimeter minus each side. And these are all multiplied together. So again, you want to have the law of cosines and Heron's formula on your note cards because they'll come in handy. We're going to be working through quite a few different problems here. Make sure you have your calculator ready because we're definitely going to be using that. For our first example, the thing that we want to do is we want to look at a picture, kind of get an idea of what we're working with, and then kind of try to decide why we're not using law of sines. We don't always have a choice whether we use law or cosines to get started, but sometimes we do later on in a problem. So let's go ahead and look at why we can't use law of sines for this first one. So this one says solve the triangle, and solve the triangle means find all sides and all angles. So again, we're looking at this and we're thinking, okay, why do I have to use the law of cosines? Well, first of all, if we draw this out, we don't know any angle at all. So that means in order to use the law of sines, I need to know one side and its opposite angle. I don't know any angles at all, so obviously law of sines isn't going to work here. These are three known sides, so this is called side, side, side. And for side, 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 I definitely use the law of cosines. So let's go ahead and look at sides and angles. We haven't started talking about any of these interesting characteristics about a triangle's angle and side relationships, but when we get done with this one, we'll be able to see some really interesting things. Okay, so I can't use the law of sines because I do not know any angles, much less a side and its opposite angle. So what I want to do here is I want to just choose one of these to solve for. Okay, so I'm going to solve for angle A. Okay, so if we solve for angle A, the formula I'm going to want to use has to start with an A over here. So A squared equals B squared plus C squared minus 2BC cosine of angle A. Now angles are capital. So let's plug in what we know. We know a squared is 22.8 squared, quantity squared. B squared is 15.1 squared. C squared is 30.1 squared minus 2bc cosine A. Now what we have to be really careful of here is do not round until you get to your final answer. Okay, so do not round. Because if you start rounding too soon, it's going to throw your final answer off. So we don't want to round at all. So the way I'd like to work this problem is not coming up with any decimal approximations or expanding this at all. I would like to just simply work through this, trying to solve for cosine A. So the way I'll do this is I'll subtract over the 15.1 squared, subtract over the 30.1 squared. So what I end up with right here would be 22.8 squared minus 15.1 quantity squared minus 30.1 quantity squared equals negative 15.1 times 30.1 cosine of angle A. Now if I want to solve for cosine of angle A, I need to divide both sides through by all of this. And again, I'm not finding any decimal approximations. If you want to, you can, but again, that might throw off your final solution. So I think it's better just to leave it out in full form right now. So we have canceling occurring here. And then you get cosine of A equals 22.8 squared divided through by negative 2 times 15.1 times 30.1. Now we want to solve for A here, not cosine A. So to finish this off, I need to go ahead and take the inverse cosine of both sides. And this is what we'd plug into the calculator to figure out what we have going on here. So when you plug it in, you have to be really careful about what's in the numerator and what's in the denominator. So I think this is an instance where we definitely want to use that fraction key. So let's go ahead and plug this into our calculator. So I'm going to start with the arc sine or the inverse cosine, or sorry, arc cosine or inverse cosine. I'm going to use the alpha y equal key to make sure I get this put in correctly. And I have 22.8 squared minus 15.1 squared minus 30.1 squared. That's the numerator. Let's go down to the denominator. This is going to be a negative 2. Make sure you use the negative key and not the minus. Times 15.1 times 30.1. Oh, and I'm not sure why this is squared down here. So in your notes right here, that squared shouldn't be there. So make sure you erase that. Let's go find the calculator again. And then we'd arrow out, close parenthesis, and enter. So what this is giving us then is angle A. Now directions, let's say, are to round to the nearest tenth. And again, we never want to round till we get to our final answer. So let's go ahead and copy and paste this into our notes. Another quick thing here, if we look up top, we are in degree mode, and you have to make sure you're in degree mode if that's what you're trying to find. If you're trying to find radians, make sure you're in radian mode. So what we have here then is angle A is equal to 47.5 degrees. So that's rounded to the nearest tenth, so 47.5 degrees. Now if we look at this table, again, this left-hand column is what is given to me to work this. I have to find everything on the right, but notice we now have a side and its angle opposite. So I could start with using the law of sines here. But if I use the law of sines for this, I'm using 47.5 degrees. And that could be wrong. I don't think it's wrong. but it could be wrong. And so that's an example of one of the reasons we always want to go back to the work and the numbers that is given to us instead of the values that we determine, because we could have a mistake there. So let's go ahead and look at finding angle B. So if we want to find angle B, we definitely could go with the law of cosines. That would be b squared equals a squared plus c squared minus 2ac cosine of b. And we can just go ahead and plug in our numbers. When we're plugging in our numbers here, we have b squared, that was 15.1, squared equals a squared, which was 22.8, plus c squared, which is 30.1, minus 2 times a times c times the cosine of b. And what I'm going to do is I'm going to go ahead and solve for cosine c, and then cosine b, and then I'll solve for b by taking the inverse cosine of each side. So let's kind of go ahead and look at this one, same as we did last time. What I'll do is I'll subtract these two over to get started. So I'll end up with negative 2 times 22.8 times 30.1. Now if you want to multiply these together and write down the full answer, that's great. But what you don't want to do is multiply those together and then round, because again you'll introduce too much rounding error. And this would be equal to 15.1 quantity squared minus 22.8 quantity squared minus 30.1 quantity squared. Now this is times the cosine of b. I'm going to scoot these over because I've dropped the cosine of b. And then we'll divide both sides through by negative 2 times 22.8 times 30.1, negative 2 times 22.8 times 30.1. So again, these cancel, and I have cosine of b is equal to everything that's on the right there. Now when we plug this into the calculator, we want to kind of look ahead and think, okay, I need to figure out what b is. I want to know what b is. So I actually need to take the inverse cosine of each side. So b would be the inverse cosine and let's go ahead and plug that in. We're in degree mode, so let's keep that in mind. So arc cosine or inverse cosine, I'm going to use the fraction key, alpha y equal. If you don't use the fraction key, I'll show you what we'll do with that. If you don't use that fraction key, you have to make sure you have parentheses over the entire numerator and the entire denominator. So 15.1 squared minus 22.8 squared minus 30.1 squared. Move to that denominator, it's going to be a negative 2 times 22.8 times 30.1. So we're in degree mode, so this is equal to 29.22548195. I want to show how you'd enter this without using that fraction key in case your calculator doesn't have that. Let's go ahead and go second inverse cosine, and then I'd open a parentheses to put in the entire numerator. 15.1 squared minus 22.8 squared minus 30.1 squared. Then I'd close parenthesis, divide, and then I'm just going to open parentheses here to make sure I get everything into the denominator. Negative 2 times 22.8 times 30.1. Close the parenthesis for the denominator, close the parenthesis for the inverse cosine, and let's see if these are equivalent. And they are. So let's go ahead and paste this into our lecture. And I think we rounded the last one to the nearest tenth. So if we rounded this one to the nearest tenth, I would get angle B equals 29.2 degrees. So let's go ahead and record that. Angle B equals 29.2 degrees. Okay, so I want to look at this again another way. So we use the law of cosines. So I had to use the law of cosines to get started. But I'm wondering is, can I switch to the law of sines? So let's go ahead and find angle B using law of sines. Okay, so law of sines, if you remember, I had sine of A over side A equals the sine of B over side B. So sine of A, if we scroll up here, was 47.5 degrees. So this is the sine of 47.5 degrees. Side A is 22.8 equals the sine of B over side B, which was 15.1. So this one, when I cross multiply and divide, what I end up getting is 22.8 sine of B equals 15.1 times the sine of 47.5 degrees. Divide both sides through by 22.8. I have some canceling occurring here, and I have the sine of B equals 15.1 sine 47.5 degrees over 22.8. So what we're going to do is we're going to take the inverse sine, or the arc sine, of both sides, just like we did for the inverse cosine. And we'll see on the left the inverse sine and the sine are inverse operations of each other, so I'm just left with the argument, which is B. And then over here on the right side, let's see what we get. So I'm going to do inverse sine, second inverse sine. I'm going to go ahead and use my fraction key. So I'll have 15.1 times the sine of 47.5 degrees. I'm in degree mode right here. I'm going to take that last parenthesis. No, I'll leave that on. And then over 22.8. Now I'll put in that last one. 29.22789. If you notice, let's paste that in real quick, and then I'll show you what the similarity is. And maybe you've already noticed. I get 29.2 degrees for angle B. And that's exactly the same thing we got up here using the law of cosines. So once I start my triangle and I get an, like side situation, and I find an angle, I could start with the law of sines for my next side or my next angle. I could also use law of cosines. Point being, it doesn't really matter. I kind of think I would be more comfortable using the law of cosines, just because to use the law of sines I have to rely on an angle, 47.5 degrees, that I just came up with, and it could have been wrong. So the last thing we need to do is find angle C. Well, angle C would just be 180 degrees minus these two angles. So let's go ahead and find angle C. So again, 180 degrees minus 47.5 degrees minus 29.2 degrees. So let's go ahead and subtract those. So I'd have 180 minus 47.5 minus 29.2, and I have 103.3 degrees. So angle C equals 103.3 degrees. Now I could have used the law of sines or the law of cosines to find that angle C, but again it's really just a lot easier to look at the sum of the three angles has to be 180. So we finished filling in this table here, and this is solving a triangle because I have found all three angles given all three sides for this particular case. So again, lesson learned here, you have to start with the law of cosines for your first step. For your second step, you could have used the law of sines or the law of cosines. It doesn't matter, but the whole key is do not round. Okay, because if you round, you're going to introduce error into the problem, and if you do that, it kind of compounds itself, so by the time you get to your final answer, it could be way off of where it should be. Okay, let's go ahead and look at another example. The one we just looked at again was law of cosines. It was side, 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 so I had three known sides. This next one, they give us a picture to work with, a sketch, so that makes it a little bit easier. And they want us to solve the triangle, and they would like us to round the lengths of the sides to the nearest tenths and the angles to the nearest degrees. So it'll be important to remember the rounding rules. So one thing that we could do with this is I could summarize this in a table, sides and angles. So the sides I know are A equals 6, B equal 4, and C equal, I don't know, trying to figure that one out. And then angle A, I don't know. Angle B, I don't know. And angle C is 95 degrees. So what I'm going to do is I'm going to go through these real quick and highlight them just so we can see what was given. So the highlighted values are the ones that were given in the problem. And as soon as you see this setup, you'll notice right away that we never know an angle in its opposite side. So C is 95 degrees, but we don't know its opposite side. A and B have a length of 6 and 4, but we don't know their opposite angles. So the thing we need to remember here, I don't have what it takes to set up the law of sines. And usually it's easier to look at that than it is to try and figure out, you know, do I have side angle side, 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 etc. But for this one, we can clearly see I have a side, I have an angle, and a side. So this is side angle side. This would be law of cosines. Okay, so I think the first thing that we can do is we could probably find side C. So let's go ahead and find side C. So that's going to be C squared equals A squared plus B squared minus 2AB cosine of C. So let's go ahead and populate that. C squared I don't know. 6 squared plus 4 squared minus 2 times 6 times 4 times the cosine of 95 degrees. Okay, so this one we don't need to divide or anything to solve. I just need to go ahead and plug this directly in. And then once I have it plugged in, I need to remember to take the square root of both sides because I don't want to solve for C squared. I would like to solve for C. So let's pop open that calculator. So this is going to be 6 squared plus 4 squared minus 2 times 6 times 4 times the cosine of 95 degrees. And I am in degree mode. So I get C squared equals 56 point, etc. Whoops. Let me see if I can get that popped in again. So 56.18347.565. Now something I want you to remember here, in order to solve for C, I need to take the square root of this. I don't want to round this to, let's say, 56 or 56.2. I want to keep all these values because if I round, I'll introduce rounding error. So we'll figure out the square root of this. Now from here, when you have your calculator open, I don't want to do second square root and then have to enter this whole thing again. So the easier thing to do is to take this number and raise it to the 1/2 power, because an exponent of 1/2 is the same as the square root. So I'll do exponent, and notice it fills in my last answer to the 0.5. That just saves you a little bit of a step. Enter, and 7.4955, etc. is my answer for C. Now instructions here, I believe, it says the lengths of the side to the nearest tenth, so this would be 7.5. So this is C squared, and this is C. So C is approximately equal to 7.5. Okay, so this is 7.5. Now from here, I could use the law of sines if I wanted. If I wanted to use this ratio right here, or I could solve for A or B next, angle A or angle B, and I'm going to stick with the law of cosines. So I would like to find find angle B. And you could find angle A just as easily, but I'm going to do angle B. So to find angle B, I'd want to do B squared is equal to A squared plus C squared minus 2AC cosine of B. So I populate this for what I know. I'm going to have to use that 7.5 that I just found for C. And cosine B, I'll need to solve for that first, and then after I find cosine B, I can take the inverse cosine of both sides to find out what angle B is. So again, I'll subtract these two over, so I'll have -2 times 6 times 7.5 cosine of B equals 4 squared minus 6 squared minus 7.5 squared. So we're going to divide both sides through. -2 times 6 times 7.5. So these cancel. I have cosine of B equals 4 squared minus 6 squared minus 7.5 squared. And then to solve for B, I take the inverse cosine of each side, so I get B equals inverse cosine. And I guess another reason I don't multiply these out, again, you might have a decimal with 5 or 6 digits, and I'd have to copy them all down. But another thing is I start to see these patterns. And these patterns, again, I can see the sides on the top divided that same pattern every time. So let's go ahead and plug this into the calculator and see what we get. So I'll get B equals So I'll have second inverse cosine. I'm going to use my alpha y equal, my fraction key. That'll make sure I have everything in the correct numerator denominator. If you don't use that fraction key, you need to make double sure that you have the entire numerator in parentheses divided by the entire denominator in parentheses. Arrow out, close parenthesis, 32.089. So in this particular case, angle B then would equal 32 degrees, because I think they told us to round degrees to the nearest whole degree. So this would be 32 degrees. Okay, and that came from right down here. And then I should be able to find angle A pretty easily. Angle A is going to be 180 degrees minus 95 degrees that was given to us minus 32 degrees that we just found. So let's look at 180 minus 95. minus 32 degrees. That's 53 degrees. So if we come up here and fill in that 53 degrees, okay, I think we've got it 32.089. I think I copied it down wrong. So that would be 32 degrees. So this is just 32 degrees up here. Now if I add 53 plus 32 plus 95, I do get 180, so that's a nice checkpoint. So that's again solving. I could have used law of sines as well to find angle B, and it totally doesn't matter, but the whole key is do not round to your final answer. Now let's notice a couple interesting things about here. The shortest side is 4. The shortest angle is opposite that at 32. So shortest side, shortest angle are the same. Longest side, largest angle are opposite each other, and that's always going to be the case. Also, quick note, if you take any two sides, 6 plus 4, it should always equal more than the third side. 4 plus 7 plus 5, or sorry, 4 plus 7.5 would be 11.5, which is more than 6. So again, if you take two sides of a triangle and add them together, it'll always be more than the third side. So I think we've gone through angle, side, angle, and side, side, side. So most of the problems will be pretty straightforward from here. Now one thing that we'll want to do is go ahead and set up a few of the application problems to help you out. So for this example, it says we have a triangle-shaped swimming pool. It's a little distorted there. A triangle-shaped swimming pool. So the best bet would probably be to draw a triangle. Now when you sketch these, we don't always know before we get started which is going to be the largest angle, which is going to be the longest side. So don't worry about that. Let's just make sure we get it filled in correctly. So a swimming pool, triangular swimming pool, measures 46 feet on one side and 32.7 feet on the other. Now if you chose to put the 32.7 over here, that's fine. What matters then is once I have those two sides set up, the two sides form an angle of 40.6 degrees. That's what matters. The 40.6 can't go up here because it's not formed by this other 32.7 side. So it can't go here. It can't come down here because it's this other leg right here doesn't help to form that angle. So it says the two sides form an angle. So this is the angle formed. So that'd be 40.6 degrees. So if you notice then, once I have this set up, this is side, angle, side. So again, side, angle, side. Side, the enclosed angle, and the other side. Well, side, angle, side is the law of cosines. And again, you can see that we're not going to use law of sines here because I do not know an angle in its opposite side, and I need to know that in order to work with the law of sines. Now, you can figure it out from here, but you're basically trying to find this side C. And you can label the sides. Usually it's pretty helpful. You could do A. This would be C, B. Side B would be B equal 46. Side A is 32.7. So you can set that up and you find side C. So the length of the third side is 30 feet, and that's rounded. And I'm going to let you set it up and find that, but I just wanted to sketch out the picture for you so you were kind of aware of how you can work through those once you get them set up and sketched. Let's go ahead and look at another example, and again I'm just going to set a few of these up and I'll leave it to you to solve for these. And if you ever get stuck while you're trying to solve, of course feel free to send me a screenshot or send me your work and I'm happy to help you work through the problem. Okay, we have a ship is sailing east, so east is marked right here. North is straight up. Now south, of course, would be below the north. Now it says that at one point the bearing of a submerged rock is 46 degrees 20 minutes. So this is our first locate. The 46 degrees 20 minutes, if you'll recall, if I'm not given a north, 46 degrees east or something like that, I always do this from the vertical north-south line. So this piece right here is the 46 degrees 20 minutes. Now also over here, I'll put in this north-south line. What we have here from this point, moving from, again, this vertical line all the way around to this bearing line, is going to be 308 degrees 40 minutes. Now that's not saying that this smaller angle right here is that's all the way around. So a couple things we need to do. We need to find this angle. I should be able to do that pretty easy because I see that this is a 90-degree angle. And then I should be able to find this angle as well because I know there's 360 degrees in a full circle. I know that this is a 90 as well. So again, those pieces of information will help me figure out what's going on here. So the first one I want to do is I want to find that first angle. So I know that's a 90-degree angle, so I want to take 90 degrees minus 46 degrees 20 minutes. So if I subtract 90 degrees minus 46 degrees 20 minutes, I'll try that again. 46 degrees, 20 minutes. I end up with 43 degrees, 40 minutes. So this is 43 degrees, 40 minutes. I think I'm going to have to draw this picture a little bit bigger. Kind of running out of space. So this is now 43 degrees, 40 minutes. This is 14.7 miles. And now this one over in the corner is going to be a little bit tricky. So this is my second angle. So for the second angle, if I just draw a picture of the vertical line, I guess I should put this in as dash so it kind of matches. This value is here, and I have a bearing to the rock. So what happens is I have this 308 degrees 40 minutes. So with the 308 degrees 40 minutes, that will start right here. And then what I could do a couple things. If I wanted to figure out what this angle is right here, I could look at the part that I don't want. So I don't want this, that's a 90. I don't want this, that's another 90 for 180. And I don't want this, so that's another 270. So I could take 308 degrees 40 minutes minus 270 degrees. Okay, so we have 308 degrees (40 minutes) minus 270 degrees. Degrees, not minutes here. So I get 38 degrees 40 minutes. So this is equal to 38 degrees 40 minutes. So this would be 38 degrees 40 minutes. Now if you notice here I have angle, side, angle, which is the law of cosines. So again, angle, side, angle. So from here what we're trying to figure out, it says find the distance of the ship from the rock at the latter point. So here is the latter point, here's the rock, so I'm trying to find this distance right here at C. So I'm going to let you go ahead and set that up and solve, and again you just have to make sure you label your triangle correctly. It's going to be fairly straightforward. One of the things I want to make sure that I do is I want to make sure I set up a lot of different types of problems for you so you don't get stuck. So if you solve for this, we are going to get C equal 10.2 miles. So when you get done, you'll get c equals 10.2. And again, if you get stuck while you're working on that, it's no problem. Go ahead and take a screenshot of your work and send me a text, and I'm happy to help you out. I'd like to set up another problem for you. And again, I'm setting these up and getting you started on them because they're a little bit more difficult maybe, and sometimes it's hard in an online class or in a class where you can't get help right away when you need it. So I want to make sure you have a lot of examples to work with. Okay, so for this one it says a weight is supported by cables attached to both ends of a horizontal beam, as shown in this figure. What angles are formed between the beam and the cables? So I have this angle that's on the left and this angle that's on the right. So to get started, I think what I would like to do is to think about this larger triangle right here. So I have this large triangle. Oops. I'll draw that in first and then put in the point. So I have 35 feet, I have 60 feet, and I have this 90 feet. Now in here, this altitude drops, and I do have a 90-degree angle here. I don't know if that's going to be useful or not, but for now, let's go ahead and look at this in terms of side, side, side. So if I label this triangle, I'm going to call this A, side A, B, side B, C, side C. So when we set this up, I am basically trying to figure out what this angle A is right here. So can I use the law of sines or the law of cosines here? Well, to get started, I don't know any angles. I don't know A, I don't know B, I don't know C. You might say, well, you know these two 90s, but they don't count, they're not part of that larger triangle. So what I can do here then is I can look at this triangle in terms of side, 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 which is law of cosines. So once I set this up as side, 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 law of cosines, I should be able to find angle A. And I would use A squared equals B squared plus C squared minus 2BC cosine A. And what I'm going to do is populate this, solve for cosine A, and then I'll take the inverse cosine of each side. And what I end up with here then is this angle A that I have would be 25 degrees, rounded of course. So solutions, angle A is 25 degrees, and then angle B would be 14 degrees. Now if you wanted to find angle C, you could do that as well, but it's not being asked for. What it's asking for, what are the angles formed between the beam and the cables? So that's this A and this B. So again, I'll allow you to go through. I'll have you work on this one yourself to make sure you can match those solutions. But again, if you get stuck, please let me know because I'm happy to help with these. Now this next one is a little tougher. We're given a baseball diamond, and this is kind of squished so it doesn't look quite like a diamond, but we'll go ahead and look at some of the characteristics that were given over here. It says a baseball diamond is a square 89 feet on each side. So each of these sides is 89 feet, and because it's a square, what we know is we have these 90 degrees in the corners. Now notice this angle right here does not go straight across, it dips down toward the pitcher's mound. However, this does come straight down and it does bisect that top angle and that bottom angle both. Okay, so now next we want to do is to figure out we see four little triangles that make up this baseball mound. So let's go ahead and try to focus on which one we're going to be looking at first. Now one thing they tell us that the pitcher's position from home plate, so this distance from here to here is 60.5 feet. Okay, so let's go ahead and label what we have here and see how to get started. And again, I'll get you started on this, but I'll have you finish it up as well. Otherwise, this would be like a two-hour video or some crazy thing because they do take a lot of work. So what we want to do is we want to find this distance from second base to home plate. So this is the triangle that I'm looking at right here. So this is a 45-degree angle, this is a 45-degree angle because remember they were bisected, and this is a 90-degree angle, and that's shown right here. This is 89 and 89, which totally makes sense because I have two equal angles, I have two equal sides. And so what I want to do is I want to find this distance. Again, this is 60.5 here. I want to find this distance from here to here because I'm supposed to find the distance from the pitcher's mound to each of the bases. So I'm going to find second base first. Now I can't really just find just this piece from here to here. I'm going to call it X, I guess. But I can find the piece from here down to here. So for this one, to get started, I'm not going to use the law of sines or the law of cosines. I'm going to use Pythagorean's theorem. So let's call this h, this distance. So if you notice, that's the hypotenuse. So I'm going to use Pythagorean's theorem, so leg squared plus leg squared equals that hypotenuse squared. So h would be the square root of 89 squared plus 89 squared. So let's go ahead and see what h would be. And again, that's second square root, 89 squared plus 89 squared. So this is equal to 125.8650071. Now you have to be careful about rounding. Make sure you don't round to the very end. So if I know that this total distance, h, is 125.8650071, I could subtract the distance from home plate to the pitcher's mound to figure out the distance from pitcher's mound to second base. So let's go ahead and take that 125.8650071 and subtract 60.5. So I get 65.365.00705. Now directions will probably say something like round to the nearest tenth. So the pitcher's mound to second base would be 65.3 feet to get us started. So this is 65.3 here. Okay, so from here, now I should be able to find the distance from the pitcher's mound to first base because now I have two sides. Okay, I can't say that this angle is a 45 anymore because it's not coming straight across, it's dipping down. But this is a bisected 45, so I should be able to use that. So, to first base, to second base, and to third base. Well, second base we just found it was 65.3 feet. Actually, it'd be 65.4 feet because the next digit is a 6, so 65.4 feet. And then when you get done for first base, it should be 63.0 and 63.0 to third as well. And the reason that would be is the similar triangles. So go ahead and work through that. This would be a good problem to show up on a handwritten homework. I just don't want to take time away from setting up a few other problems to totally go through this because it would take quite a while. Now the only type of problem we haven't done yet is Heron's formula for the area of a triangle with three sides known. So let's go ahead and look at that as our last problem. Okay, so use an appropriate area formula to find the area of the triangle with the given side lengths. So we're going to use Heron's formula for the area of a triangle with three known sides. Now the first thing we know, or the first thing we need to figure out, is that S value. Now if you recall, that is semi-perimeter. So semi-perimeter is equal to S, which is 1/2 times A plus B plus C. So S is 1/2, 14 plus 10 plus 19. Now here we're probably going to have a fraction. 14 plus 10 plus 19 is 43. 43 divided by 2 is 21.5. So to find the area, that's going to be the square root of 21.5, the semi-perimeter, times the semi-perimeter minus each side. And again, this is under the square root sign. So I'm just going to go ahead and plug this into my calculator. So this value under the radical is 4635.9375, and I want to take the square root. So if you're using your calculator, that's really nice if you can take it to the 0.5 power. And I get 68.08771916. So if we round that to the nearest tenth, it would be 68.1 square meters in this case. Okay, so law of cosines, very, very long sometimes. Make sure you set up a picture or a table to help you work through these. It'll help you organize your work. If you have any questions while you're working, please let me know, and as usual, I'm happy to help you out. Just send a text of the problem and or a text of your work as well. Good luck.